Hello there, and welcome to the Sleepless Scientist, a gentle corner of the night where questions are allowed to unfold slowly, without pressure, and where learning is meant to feel like a warm, steady breath rather than a test. Tonight, we're going to explore something that seems simple at first glance, almost ordinary, and yet quietly reshapes everything we believe about reality itself: the speed of light. You might think of light as something obvious. It fills the room when you flip a switch. It spills over rooftops at sunrise. It arrives so reliably that we almost never think about it arriving at all. And yet, hidden inside that familiarity is a limit so fundamental that it bends time, stretches space, and draws invisible borders around cause and effect. Before we begin, if these slow explorations help you unwind, you're welcome to like this video or subscribe only if it feels right. And if you feel like it, leave a comment telling me where in the world you're listening from and what time it is for you right now. It's always comforting to imagine all of us scattered across the planet sharing the same quiet curiosity, even if we're not sharing the same moment. Now, as you settle in, maybe let your shoulders soften a little, let the room dim, or let the screen glow gently without demanding attention. If your thoughts wander, that's perfectly fine. You don't need to hold on to every sentence. This is a story meant to drift, and you can drift with it. Tonight's journey begins not with equations or experiments, but with a simple feeling most humans once shared: the feeling that light had no speed at all. For most of human history, no one believed light needed a speed, not because people had proven it was infinite, or because they had carefully tested it, but because everyday life made it feel unnecessary to ask. Light simply appeared. A torch was lit and the cave brightened. The sun rose and the land was already glowing by the time anyone noticed. Lightning flashed, and the flash itself seemed inseparable from the event. There was no pause, no waiting, no sense of travel. To the human nervous system, light felt immediate in a way sound never did. Thunder arrived late. Echoes bounced back slowly from distant hills. Voices faded with distance, but light behaved differently. It seemed to erase distance altogether. This quiet assumption shaped how people understood reality itself. If light was instantaneous, then seeing and happening were effectively the same thing. To observe something was to be present at the moment it occurred. There was no hidden delay between the world and your awareness of it. The universe, as far as the senses were concerned, unfolded in a shared now. This wasn't carelessness. It was practicality. The human body is not built to notice delays measured in tiny fractions of a second across everyday distances. Even if light does take time to travel from one side of a room to the other, that time is so unimaginably small compared to human reaction speed that it vanishes into the background of perception. In daily life, this creates a powerful illusion. When you open your eyes, the world seems to appear all at once. When you look at someone's face, you don't experience a sense of information arriving from different parts of the room at different times. The scene feels unified, present, and complete. That feeling became the foundation of early thought. Long before experiments, before instruments, before mathematics capable of handling extreme speeds, philosophers tried to describe the nature of light using intuition alone. And intuition insisted that light was not a thing that moved, but a condition that simply existed. Darkness was absence. Light was presence. It did not travel into a space. It revealed a space. In this way of thinking, asking how fast light moved made about as much sense as asking how fast daytime travelled. This perspective was not foolish. It was deeply human. Even today, your brain still operates as if light were instantaneous. When you catch a falling object, when you navigate a doorway, when you read words on a screen, your mind assumes that what you see corresponds to what is happening right now. It corrects for sound delays automatically, but it does not correct for light, because for most of your life, there has been nothing to correct. And so for centuries, light was treated as a kind of cosmic messenger, with no travel time, no fatigue, no journey. It was simply there, bridging distances effortlessly, erasing separation between observer and event. This belief quietly shaped deeper ideas as well. If light had no speed, then time itself felt absolute. If everyone saw the same events at the same moment, then now belonged to the entire universe. There was one shared present, flowing forward uniformly, like a river that carried all observers together. Distance mattered for travel, for sound, for effort, but not for sight. Sight seemed privileged, almost sacred. To see was to know immediately, and because no one noticed any cracks in this picture, no one felt urgency to challenge it. Not at first. The first doubts did not come from laboratories or universities, but from a subtle discomfort that grew as human curiosity stretched farther than daily experience. As people began to look not just across rooms or fields, but across vast distances, something strange began to emerge. The heavens were not nearby. The stars were unimaginably far, and yet they still appeared instantly, fixed, steady, present. If light truly had no speed, then distance, no matter how enormous, made no difference at all. That idea felt comforting in a way. It suggested a universe that was fully available to observation, worm and cosmos that revealed itself without delay or secrecy. The sky, no matter how deep, was always now. But comfort is not the same as truth. The moment humanity began to ask more precise questions, to notice patterns that unfolded over time, to compare distant events against moving clocks, the assumption of instant light would begin to feel less secure. Very slowly, almost reluctantly, the universe would reveal that what felt immediate was not always what was real. Yet at this early stage, none of that tension was visible. The illusion held firm. Light appeared to have no speed because it did not need one, at least not in the human scale of life. Reality seemed kind enough to meet us where our senses were strongest, and for a long while we accepted that gift without question. As this quiet certainty settled into human thought, it set the stage for a profound surprise. Because the moment light was finally asked to reveal its true nature, it would not simply answer a technical question. It would challenge the very ideas of time, distance, and simultaneity that had shaped human understanding for thousands of years. When ideas feel obvious, they rarely feel fragile. For centuries, the belief that light was instantaneous did not exist as a loose assumption. It was anchored, reinforced, and given intellectual weight by one of the most influential thinkers in human history. Aristotle did not merely describe light as instant. He framed it as something that could not meaningfully be said to move at all. In Aristotle's view, motion required a medium and a process. Stones fell, arrows flew, smoke drifted. These were things that occupied space as they moved through it. Light, however, did not behave like that. When a flame was uncovered, illumination appeared everywhere at once. There was no sense of light crossing the room, no visible wave advancing across space. Darkness vanished, replaced by presence. From this perspective, light was not a traveller. It was a state. Darkness was potential, light was actuality, and when actuality appeared, it did so immediately. This idea fits seamlessly with daily experience. It also fit beautifully into a broader philosophical system that emphasized purpose, essence, and natural order. Aristotle's world was one in which things behaved according to their nature, not according to hidden mechanisms waiting to be measured. And because Aristotle's writings shaped education for nearly 2,000 years, his description of light carried extraordinary authority. It wasn't simply one opinion among many. It became the default explanation taught, repeated, and preserved across generations. But what made this belief so durable was not just Aristotle's influence, it was the absence of contradiction. There were no clocks fast enough to challenge the idea, no distances within reach that could reveal delay, no experiments sensitive enough to separate very fast from instant. As long as human observation remained grounded in everyday scales, light's behaviour offered no reason to doubt its immediacy. In this way, philosophy filled a gap that technology had not yet learned how to open. The ancient world did not lack curiosity, it lacked tools, and without tools, even the most thoughtful minds were forced to trust what perception suggested most strongly. Vision, after all, feels authoritative, it feels direct. We rarely question it, even now. Imagine standing at the edge of a field at dusk. A torch is lit on the far side. You see it the moment it ignites, no waiting, no delay. The experience feels complete, synchronized, shared. That feeling becomes evidence, even when no measurement has taken place. So light remained special. Sound was slow. Touch required proximity. Smell drifted unpredictably, but sight seemed to erase distance. It connected observer and object as if space itself were irrelevant. Within Aristotle's framework, this made sense. Light didn't move through space because it didn't need to. It revealed space. Over time, this idea quietly shaped how people thought about time itself. If sight connected everyone to the same events instantly, then time could be imagined as universal. One present moment, shared across the world. A single now that everyone inhabited together. This concept was never stated as a formal law. It didn't need to be. It was embedded in how people talked, taught, and reasoned. The universe felt synchronized because perception made it feel that way. And so the question of light speed remained unasked. Not because it was forbidden, but because it seemed unnecessary. Why measure something that did not appear to travel? Why assign a speed to what felt like an on-off condition of reality itself? There were, of course, whispers of doubt. Some thinkers wondered whether light might require time to reach distant places. Others speculated that perhaps its speed was simply too great to notice. Yes, but without a method to test these ideas, they remained philosophical curiosities, not challenges. In a culture where authority mattered deeply, speculation without proof struggled to gain ground. Aristotle had provided a coherent picture, and no clear evidence demanded revision. This is not a story of ignorance, it is a story of stability. Human understanding often rests not on what is most accurate, but on what works well enough for the questions being asked. For everyday life, for navigation, for agriculture, for architecture. The idea of instantaneous light caused no problems at all. It took a very specific kind of question to expose the cracks, a question that stretched beyond human-scale distances, a question that asked not how light behaves in a room or a field, but how it behaves across vast separations, where even the smallest delays might accumulate into something noticeable. That question would not arise from philosophy alone. It would require observation, patience, and a willingness to trust data over intuition. And so, Aristotle's shadow lingered, not because it was wrong in spirit, but because nothing had yet forced it to step aside. The belief in instantaneous light remained comfortable, unchallenged, and deeply woven into the human sense of how the world revealed itself. But comfort has a way of dissolving when precision enters the picture. As humanity's gaze slowly lifted from Earth to the sky, from nearby objects to distant rhythms, light would finally be asked to do something it had never been asked to do before. It would be asked to arrive late. Eventually, curiosity outgrows comfort. For centuries, the idea that light was instantaneous remained undisturbed, not because it was proven, but because no one had yet found a way to question it properly. That began to change in the early 17th century, when a new kind of thinking started to take root. Instead of asking what must be true, some thinkers began asking what could be tested. Among them was Galileo Galilei. Galileo lived at a moment when the universe was slowly becoming an object of measurement rather than reflection alone. He had already challenged long-held ideas about motion, falling objects and the heavens, and at some point the question arose quietly but persistently. If light really does move, could its motion be detected? Galileo's idea was simple, almost charming in its directness. He imagined two people standing far apart on hilltops at night, as each holding a lantern. One person would uncover their lantern, and the moment the other person saw the light, they would uncover theirs in response. By measuring the time between uncovering the first lantern and seeing the return signal, Galileo hoped to detect a delay. If light took time to travel, even a very small amount, perhaps it could be measured. This was not a careless thought. It was an honest attempt to bring light into the same experimental framework as sound and motion, and importantly, it reflected a new willingness to accept that human intuition might be wrong. So the experiment was tried, lanterns were uncovered, signals were exchanged, timing was observed as carefully as possible, and the result was nothing. No measurable delay. The return light seemed to arrive instantly. At first glance, this appeared to confirm the old belief. Light once again seemed to have no speed worth discussing. But Galileo did not treat this outcome as a final answer. He recognized something subtle and important. The experiment had not shown that light was instantaneous. It had only shown that any delay was too small for humans to detect using their own senses and reaction times. This distinction mattered. Human reaction time is slow. Even the quickest response takes a fraction of a second. And light, as we now know, crosses kilometers in far less time than that. Galileo was not measuring light so much as he was measuring himself. In that realization, something profound happened. The failure of the experiment revealed not the nature of light, but the limits of human perception. It showed that there were phenomena operating beyond the scale at which our bodies could directly intervene. This was a quiet turning point. For the first time, the question of light speed was no longer philosophical. It had entered the realm of experimental science, even if the tools were not yet adequate. Galileo had asked the right question too early. There is something deeply human about this moment. Science often advances not by getting answers, but by discovering better questions. Galileo's lanterns did not measure light, but they illuminated a gap between the world as it feels and the world as it is. Light might still appear instantaneous, but now there was a reason to suspect that this appearance could be misleading. In a way, this experiment planted a seed of doubt that could not be easily dismissed. If light were truly instantaneous, then no distance, no matter how large, would ever reveal a delay. But if light were merely very fast, then distance would eventually matter. The problem was not conceptual, it was practical. The hills were not far enough apart, the clocks were not precise enough, the human nervous system was not fast enough. Yet the idea lingered. Once a question has been asked sincerely, it does not disappear simply because the first attempt fails. It waits. It gathers patience. It waits for better methods, better perspectives, and sometimes for entirely different scales of observation. Galileo's experiment also marked a subtle shift in how knowledge was pursued. Authority alone was no longer sufficient. Even Aristotle's influence could be tested, at least in principle. The universe was beginning to be treated as something that could surprise us. And perhaps most importantly, this moment introduced a recurring theme that would echo throughout the history of physics: When experiments fail, they do not always fail because the idea is wrong. Sometimes they fail because the world is operating on scales we are not yet prepared to observe. Light didn't reveal its speed to Galileo, but it did reveal something else. It revealed that reality might be layered, with behaviours that only become visible when the right questions are asked in the right way. This realisation quietly changed the tone of the conversation about light. The certainty that had surrounded it for centuries began to soften. Light was no longer just a condition of visibility. It was becoming a phenomenon that might have structure, limits, and behaviour of its own. From this point forward, the problem was no longer whether light had a speed. It was how to find a situation where that speed could make itself known. The answer would not come from hills or lanterns, it would come from the sky. Far above human reaction times, far beyond human distances, the universe itself would provide a clock precise enough to reveal what Galileo could only suspect. And when that clock finally began to drift out of sync, the illusion of instantaneous light would quietly begin to unravel. When light finally revealed its speed, it did not do so in a laboratory. It didn't appear between mirrors or wheels or lanterns on distant hills. Instead, it revealed itself quietly, patiently, through the steady rhythm of the heavens. The universe, it turned out, was far better at keeping time than any human-made clock. In the late 17th century, astronomers were carefully observing the motions of Jupiter and its moons. Among them was Ole Rømer, a Danish astronomer working in Paris. His task was practical rather than philosophical. By timing the eclipses of Jupiter's moon Io, astronomers hoped to improve navigation and determine longitude more accurately here on Earth. Io was a remarkably reliable clock. As it orbited Jupiter, it passed regularly into the planet's shadow, disappearing and reappearing with predictable timing. These eclipses could be calculated and anticipated with impressive precision. At least that was the expectation. As Rømer observed Io over many months, he noticed something strange. The eclipses did not always occur exactly when predicted. Sometimes they arrived a little early, sometimes they arrived a little late, and these deviations were not random. They followed a pattern tied to Earth's position in its orbit around the Sun. When Earth was moving closer to Jupiter, the eclipses seemed to happen sooner than expected. When Earth was moving farther away, they seemed delayed. At first, this was puzzling. Io's orbit around Jupiter had not changed. Jupiter itself had not changed. The clockwork of the moon remained steady. And yet the timing, as observed from Earth, drifted. Rømer began to suspect something radical for the time. The delay was not happening at Jupiter, it was happening in the light travelling from Jupiter to Earth. When Earth was closer, the light had a shorter distance to cross and the eclipse appeared sooner. When Earth was farther away, the light had farther to travel and the eclipse appeared later. The moon was not late. The message was. This was a subtle but profound shift in perspective. For the first time, light was treated not as an instant revelation, but as a messenger that required time to deliver information across space. Rømer didn't measure the exact speed of light as we know it today. His estimate was rough by modern standards, but the significance of his work did not lie in numerical precision. It lay in the concept itself. Light, finally, had been caught arriving late. This delay was not something the human nervous system could perceive directly. No one could watch an eclipse and feel the light lag behind the event. The delay only became visible when observations were compared carefully over long periods, across enormous distances. In a sense, Rømer's discovery revealed a new kind of time. There was the time at which an event occurred, and the time at which the information about that event arrived. These two moments, which had always felt identical, were now clearly distinct. This realization quietly redefined what it meant to observe the universe. To look at the sky was no longer to witness events as they were happening, but as they had happened. The stars, the planets, the moons were not presenting the present, they were presenting the past. Even though the delay between Jupiter and Earth was only a matter of minutes, the implications stretched far beyond that single system. If light took time to cross space, then distance mattered in a new way. Space was no longer transparent. It introduced delay, separation, and history. What made this discovery especially powerful was its inevitability. Riemann did not need faster clocks or better reflexes. He let the universe accumulate delay on his behalf. Over millions of kilometers, even light could not hide its finite speed. This approach marked a turning point in scientific thinking. Instead of forcing experiments into human-scale settings, astronomers began to realize that nature itself offered experiments far larger and more precise than anything built on Earth. The sky became a laboratory. Rieman's conclusion was not immediately accepted by everyone. Some doubted the interpretation, others questioned the assumptions. But the pattern was clear enough that the idea of finite light speed could no longer be dismissed as speculation. The belief in instantaneous light had finally encountered evidence that intuition alone could not explain away, and once that door opened, it could not be closed again. From that moment forward, light was no longer timeless, it had duration. It carried information across distance at a measurable pace. The universe was no longer fully synchronized. Events happened, and only later did they become known. This change may sound technical, but it carries a gentle philosophical weight. It suggests that reality is layered. There is what happens, and there is what we see. And between the two lies a journey, however brief. As astronomers continued to refine their observations, the delay of light would become an essential part of understanding the cosmos. The stars would become records, galaxies would become archives. Looking outward would become a way of looking backward in time. But for now, the revelation was still modest. Light had a speed. It was fast, unimaginably fast, but not infinite. And that single fact was enough to unsettle centuries of certainty. With this discovery, the universe began to whisper a new truth. The world was not as immediate as it felt. Distance carried meaning. Time was no longer shared so simply. The illusion of instant reality had been cracked, not by force, but by patience. And as measurements grew more precise, that crack would widen, slowly transforming a small, astronomical delay into a complete reimagining of time and space themselves. Once light was understood to arrive with delay, the sky began to behave differently, not dramatically, not in ways the naked eye could easily notice, but subtly, persistently, and with a kind of quiet honesty that only careful observation can reveal. The universe had accepted the idea that light took time to travel, and now it began to show what that meant when motion entered the picture. In the early 18th century, astronomers were mapping the positions of stars with increasing precision. Among them was James Bradley, who noticed something strange while attempting to measure stellar parallax, the slight shift in a star's apparent position caused by Earth's movement around the Sun. Parallax was expected, aberration was not. Instead of stars shifting back and forth as Earth moved, Bradley found that they traced small, steady ellipses across the sky over the course of a year. Even more puzzling, all stars appeared to shift in the same direction at the same time, regardless of their distance. This was not the behaviour of stars themselves, it was the behaviour of light meeting a moving observer. To understand this gently, imagine walking through vertical rain. When you stand still, the rain falls straight down. But when you begin to walk forward, the rain appears to slant toward you, not because the rain has changed direction, but because your motion changes how you intercept it. Light behaves in much the same way. As Earth moves through space, it does not wait for light to arrive, it moves forward to meet it. And because light has a finite speed, this motion causes the apparent direction of incoming starlight to tilt slightly, like rain against a moving window. This effect is known as stellar aberration, but the name is far more technical than the experience it describes. But what matters is the implication. The tilt exists only if light takes time to travel. If light were instantaneous, Earth's motion would not matter at all. There would be nothing to lean into. Bradley's observation offered a beautifully simple confirmation of light's finite speed. It did not require clocks or mirrors. It did not rely on measuring delays directly. It relied on geometry and motion, on the quiet interplay between a moving observer and a travelling signal. And the result was remarkably consistent. The angle of this stellar tilt matched exactly what one would expect if light travelled at a fixed speed while Earth moved around the Sun at a known pace. The numbers aligned. The sky agreed. Once again, light behaved not as a condition but as a messenger. What made this discovery especially elegant was its universality. Tsahin, the effect appeared for every star, near or far. It did not depend on the star's distance because the phenomenon was not about where the star was. It was about how the light reached us. This reinforced a growing realization. Light speed was not just a property of light sources, it was a property of space itself. Wherever light travelled, it did so at the same pace, responding to motion in the same way. As measurements improved, astronomers began to refine their estimates of light speed using this method. The values were not perfect, but they were consistent. Each new approach, each independent observation, converged on the same conclusion. Light was fast, incredibly fast, but not infinite. At this stage, the idea of light speed was no longer controversial. It had been confirmed by celestial clocks and geometric effects alike. The question shifted from whether light had a speed to how precisely that speed could be measured. This transition matters more than it may seem. When a phenomenon becomes measurable, it becomes part of the structure of science. It can be compared, tested, refined, and eventually woven into theory. Light had crossed that threshold. It was no longer an exception to the rule of motion. It was subject to them, even if in extraordinary ways, and yet something curious lingered beneath the surface. All these measurements treated light speed as something that could be measured relative to Earth's motion. Earth moved, light arrived. The relationship between the two produced observable effects, but a deeper question had not yet been asked. Compared to what? In everyday experience, speeds are relative. A car moves quickly relative to the road, slowly relative to an airplane, and not at all relative to its own passengers. Motion always seems to depend on perspective, so what exactly was light moving relative to? Some scientists proposed an invisible background, a kind of universal stage called the ether, through which light waves supposedly travelled. In this view, light had a speed relative to that medium, and Earth's motion through it should be detectable. At the time, this idea felt reasonable. Sound waves require air. Water waves require water. Why should light be different? And so, quietly, the stage was set for the next chapter in this story. A chapter that would not merely refine the measurement of light speed, but challenge the very idea of a universal frame of reference. The stars had leaned forward just enough to show that light was not instantaneous. Soon, experiments on Earth would ask whether light could ever be said to slow down, speed up, or change direction depending on how we moved. The universe, as it turned out, had a very firm answer prepared. Once the sky had spoken, scientists began to wonder whether the same truth could be coaxed out of light much closer to home. Astronomy had revealed that light arrived with delay across vast distances, but those distances were far beyond anything a human could control. The next step was an ambitious one, to measure the speed of light directly, here on Earth, using instruments built by human hands. This was not a simple task. Light moves so quickly that even crossing a city takes only a tiny fraction of a second. To detect such brief intervals, scientists had to invent clever ways to stretch time, thus turning a fleeting journey into something observable. One of the first to attempt this was Hippolyte Fizeau in the mid-19th century. His approach was mechanical and imaginative. He sent a beam of light through a rotating toothed wheel toward a distant mirror and back again. As the wheel spun, its teeth alternately blocked and allowed the light to pass. At certain rotation speeds, something remarkable happened. The returning light was blocked by the next tooth of the wheel, rather than passing cleanly through the gap it had originally escaped from. This meant that while the light was travelling to the mirror and back, the wheel had rotated just enough to move a tooth into the beam's path. By knowing how fast the wheel was spinning and how far the light travelled, Fizeau could estimate how long the journey took. From that, he could infer light speed. There were no equations written in stone here, only careful reasoning. Light left, travelled a known distance, returned, and encountered a wheel that had subtly shifted during its absence. The delay, tiny as it was, had finally become visible. Soon after, Léon Foucault refined this approach using rotating mirrors instead of wheels. His setup allowed even greater precision. A beam of light bounced between mirrors, and the slight rotation of one mirror during the light's journey caused a tiny but measurable shift in the beam's position. This shift was small but consistent, and with patience and repetition, it could be measured. These experiments marked an important transition. Light speed was no longer inferred indirectly through celestial motions. It was being measured directly, repeatedly, and reliably within the confines of a laboratory. For the first time, light was behaving like something that could be timed, compared, and tested under controlled conditions. As techniques improved, so did accuracy. Measurements began to converge. Different methods, different laboratories, different countries all arrived at remarkably similar values. Light speed was fast but fixed, reliable, predictable. This growing agreement was comforting, but it also carried a quiet tension. In everyday experience, speeds are relative. If you walk inside a moving train, your speed depends on who is measuring. To someone standing still, you move faster than to someone seated beside you. Motion is always a relationship. So as light speed became more precisely known, a natural question emerged. Compared to what is light moving? If Earth itself is in motion, orbiting the Sun, and the Sun is moving through the galaxy, then shouldn't light speed depend on the direction it travels relative to that motion? Shouldn't light moving into the wind behave differently from light moving with the wind? To many physicists of the time, the answer seemed obvious. Light, like sound or waves on water, must travel through some medium. That medium was imagined as an invisible substance filling all of space, called the ether. In this view, the ether was absolute and unmoving. Light had a fixed speed relative to it, and as Earth moved through this ether, careful experiments should detect slight differences in light speed depending on direction. This idea was not strange or mystical. It was an attempt to preserve familiar intuition. Waves usually require something to wave in. Why should light be different? And so the stage was quietly set for one of the most careful experiments in scientific history. Before that experiment could take place, however, one more figure deserves mention. Albert Michelson, whose obsession with precision pushed light measurement to its limits. Michelson refined optical techniques to an extraordinary degree, measuring light speed with unprecedented accuracy. His work made one thing clear beyond doubt. Light speed could be measured with incredible consistency. It did not drift. It did not fluctuate. It behaved as if it were anchored to something deeper than any particular source or direction. This stability was both reassuring and unsettling. On one hand, it suggested that the universe had an underlying order. On the other, it raised a troubling question. Wait, if light speed was always the same, no matter how carefully one measured it, then perhaps it was not responding to motion in the way everything else did. The idea that light might ignore the motion of its source, or the motion of its observer, had not yet been fully confronted. But the tools were now sharp enough to force the issue. The laboratory had finally caught up to the sky. And in doing so, it prepared the ground for a result so unexpected that it would quietly dismantle centuries of assumptions about space, motion and time. The next experiment would not just refine a number, it would remove the invisible stage upon which physics believed it had been performing. By the late 19th century, light no longer felt mysterious in the way it once had. Its speed had been measured again and again, says using different methods by different people in different places. Numbers varied slightly, but the pattern was unmistakable. Light travelled at a fixed pace, unimaginably fast yet remarkably consistent. For many physicists, this was a success story. Measurement had conquered uncertainty. The universe had revealed one more of its constants. But for Albert Michelson, consistency was not the end of the story. It was the beginning. Michelson was not satisfied with close enough. He believed that nature, if measured carefully enough, would reveal subtle differences hiding beneath apparent stability. And if light truly travelled through an invisible medium, then that medium should leave a trace. The idea of the ether still felt natural at the time. Waves usually require something to wave in. Water waves need water. Sound waves need air. Light, which showed wave-like behaviour in many experiments, seemed unlikely to be an exception. If the ether existed, then it provided a natural reference point, a cosmic background against which motion could be measured. Light would move at a fixed speed relative to this ether, just as sound moves at a fixed speed relative to air. And if Earth was moving through this ether, then light travelling in different directions should behave differently. This difference was expected to be extremely small, so small that only the most precise instruments could detect it. But Michelson believed precision was exactly where physics should look next. He devoted himself to optical accuracy with almost single-minded focus. Mirrors were polished to extraordinary smoothness. Distances were measured and remeasured. Vibrations were minimized. Temperature fluctuations were controlled. The goal was simple to state, even if difficult to achieve. Measure the speed of light along one direction, then measure it along another direction at right angles, and compare the results. If Earth were moving through the ether, light travelling with that motion should take slightly less time than light travelling across it. The difference would be tiny, but it should be there. Michelson's confidence was not reckless. It was grounded in everything physics had learned so far. The expectation of a difference was not controversial. It was almost inevitable, given the assumptions of the time. This is what makes the coming result so powerful. Before it arrived, the logic felt airtight. Earth moved. The ether stood still. Light travelled through it. Therefore, light's measured speed should change depending on direction. To test this, Michelson devised an instrument that split a beam of light into two perpendicular paths. Each beam travelled out, reflected back and recombined. If one beam took longer than the other, even by a tiny amount, their recombination would produce a detectable shift in an interference pattern. This setup was not dramatic to look at. There were no explosions, no flashes of discovery, just a quiet pattern of light and dark bands, sensitive to delays far smaller than anything a human could perceive directly. The experiment demanded patience. Measurements were repeated at different times of day and different times of year, as Earth's motion through space changed direction. If the ether wind existed, it should reveal itself eventually. And Michelson waited. He rotated the apparatus. He refined the alignment. He checked for sources of error. He accounted for temperature, vibration, and mechanical drift. Everything that could be controlled was controlled, and still the result refused to appear. The interference pattern did not shift in the way it was expected to. The difference between the two light paths was far smaller than predicted. In fact, within experimental uncertainty, there was no difference at all. At first, this was baffling. Perhaps the ether was being dragged along by Earth. Perhaps the effect was weaker than expected. Perhaps the apparatus was flawed in some subtle way. So Michelson improved it further. He collaborated with Edward Morley to build an even more refined version. The experiment was repeated with greater sensitivity, greater care, and greater confidence. The result remained stubbornly the same. Light speed appeared identical in all directions. This was not merely inconvenient, it was deeply unsettling. The experiment had not failed. The instruments had worked exactly as designed. The setup was sensitive enough to detect the expected effect, had it been there. And yet, reality refused to cooperate. What Michelson had encountered was not experimental error, but a conflict between expectation and observation. For decades, physics had assumed that space provided a universal backdrop, an invisible frame against which motion could be measured absolutely. The ether filled that role elegantly. Without it, something essential seemed to be missing. And yet, the experiment suggested that light did not care about Earth's motion at all. It behaved as if there were no background, no preferred direction, no hidden stage. This was a profoundly uncomfortable idea. If light speed was truly the same in every direction, for every observer, then motion itself might need to be rethought. Perhaps speed was not as relative as it seemed, or perhaps time and space themselves were more flexible than anyone had imagined. At this moment, no one had a satisfying explanation. There were patches and proposals, small adjustments meant to preserve familiar ideas, but none of them felt natural. They felt like repairs made after the fact. Michelson himself reportedly believed that the problem would soon be resolved within existing theory. He could not have known that his careful insistence on precision had done something far more dramatic. By removing every possible excuse for doubt, he had left physics with nowhere to hide. The universe had been asked a clear question in a language it could not misunderstand, and it had given an answer that contradicted centuries of intuition. The silence of the interference pattern was not empty, it was loaded with meaning, and in that silence, the foundations of space and time began to tremble. Sometimes the most important thing an experiment can say is nothing at all. When Michelson and Morley completed their measurements, there was no dramatic announcement, no immediate declaration that physics had been overturned. Instead, there was a quiet, uncomfortable realization spreading through the scientific community. The experiment had done exactly what it was designed to do, and yet it had failed to confirm the most reasonable expectation of the time. Light speed did not change. No matter how the apparatus was rotated, no matter how Earth moved through its orbit, no matter the time of day or the season of the year, the speed of light appeared stubbornly indifferent to direction and motion. This result is often called a null result, a phrase that can sound underwhelming, almost disappointing. But in this case, the absence of an effect was far more meaningful than any positive detection could have been. To understand why, it helps to imagine the mindset of physicists at the time. They were not fishing randomly for surprises. They were testing a prediction that followed naturally from everything they believed about waves, motion, and space. The ether was not an exotic hypothesis. It was the simplest explanation available, and the Michelson-Morley experiment was designed with care precisely because the expected effect was small, but not invisible. If the ether existed, the experiment should have seen it. The fact that it did not meant something profound was wrong, not with the apparatus, but with the picture of reality behind it. At first, this was deeply unsettling. Physics had always relied on the idea that motion could be measured against some background. Even if observers disagreed about their relative speeds, there was comfort in believing that the universe itself had a preferred frame, a kind of quiet stillness beneath all movement. The ether provided that stillness. Without it, there was no obvious answer to a simple question. Moving relative to what? And yet the experiment suggested that light did not care about any such background. It behaved as if every observer, no matter how they moved, was equally justified in measuring the same speed. This was not just surprising, it was destabilizing. For years, physicists tried to rescue the ether. Some suggested that Earth dragged the ether along with it, shielding the experiment from detection. Others proposed that objects physically contracted in the direction of motion, conveniently cancelling out the expected effect. These ideas were clever, but they felt artificial. They explained the result by adding complexity rather than revealing simplicity. They patched the old framework instead of questioning it. What made the situation especially uncomfortable was that nothing else seemed broken. All the equations of electromagnetism still worked beautifully. Light behaved exactly as those equations predicted. The problem was not with light, it was with space and time. This realization crept in slowly. If light speed is always the same, then the usual rules for adding velocities cannot apply. You cannot simply stack speeds the way you stack walking speeds or car speeds. Something else must adjust to keep light unchanged, and that something else could only be time, space, or both. This was a radical thought. Up to this point, time had been treated as absolute. It flowed at the same rate everywhere, for everyone. Space too was assumed to be rigid and universal. Distances were distances, regardless of who measured them. The Michelson-Morley experiment quietly challenged both assumptions without explicitly naming them. It did not say, time is flexible. It did not say, space can change. It simply refused to behave as expected. And that refusal forced a choice. Either light was behaving strangely for no reason at all, or our understanding of the stage upon which physics played out was incomplete. The power of the experiment lay in its simplicity. It did not rely on extreme conditions or exotic phenomena. It used mirrors, beams of light, and careful alignment. It asked a straightforward question in a straightforward way, and reality answered with silence. In retrospect, this silence was the sound of an old idea ending. The ether, once so useful, now felt unnecessary. Worse, it felt invisible in the wrong way, not merely undetected, but irrelevant. Physics had always valued concepts that explained observations with elegance. The ether now did neither. As this realization settled in, it created a strange tension in the scientific world. On one hand, nothing had visibly changed. Light still illuminated rooms, planets still moved, equations still predicted outcomes accurately. On the other hand, the foundation supporting those predictions had developed a crack. If there was no preferred frame of rest, then motion was more democratic than anyone had imagined. No observer could claim to be truly still, and if that were the case, then the universe had no single, absolute perspective. This idea felt deeply counterintuitive. Human experience insists on a sense of rest, of standing still while things move around us. The experiment suggested that this feeling was not written into the fabric of reality itself, it was written into us. The Michelson-Morley result did not immediately provide a new theory. It created a vacuum a space where old assumptions no longer felt safe, but new ones had not yet taken shape. That vacuum is often where revolutions begin. What was needed was not a small adjustment, but a new way of thinking about motion, measurement, and observation. A way that took the experiment seriously without clinging to the comfort of absolute space and time. That way of thinking would arrive soon, not from a laboratory filled with mirrors, but from a quiet office where someone was willing to follow a strange idea to its logical conclusion. After the experiment that refused to agree, physics entered an unusual state. Nothing had visibly broken. The planets still traced their paths. Light still reflected and refracted as expected. Equations continued to deliver correct predictions for countless phenomena, and yet something essential no longer made sense. The problem was not that the universe behaved unpredictably. It was that it behaved too consistently. Light speed remained unchanged no matter how carefully it was measured, no matter how the observer moved, no matter how the apparatus was oriented. The more precision scientists applied, the more stubborn the result became. This created a quiet crisis. For generations, physics had relied on a simple hierarchy. Space provided a rigid stage. Time flowed evenly across it. Motion happened within this framework. Observers could disagree about speeds, but they all measured them against the same background. The Michelson-Morley result removed that background. At first, physicists tried to save the old picture with minimal damage. Perhaps objects physically shrank in the direction they moved. Perhaps time ticked slightly differently depending on motion, but only in a compensating way that hid the ether's effects. Perhaps the ether existed but behaved in an unexpected manner. These ideas were ingenious, but they felt uneasy. They explained one experiment at the cost of clarity everywhere else. Instead of simplifying the picture, they cluttered it. The deeper issue was this. Every proposed fix assumed that space and time themselves were untouchable. They were treated as absolute, sacred structures that could not be questioned. The adjustments were always made to objects moving within space and time, never to space and time themselves. But what if that assumption was the real problem? This question was uncomfortable, precisely because it threatened something fundamental. Time feels personal. It feels like the one thing everyone shares. Space feels solid, dependable, real. To question them was to question the framework of experience itself. Yet the evidence was quietly pointing in that direction. If light speed was truly the same for all observers, then the usual way of adding speeds could not work. If you chase a beam of light, it does not slow down relative to you. It does not wait. It does not care. That behavior cannot be explained by tweaking objects alone. Something deeper must adjust to preserve light's constancy. Gradually, a new possibility began to emerge. Perhaps time does not pass at the same rate for everyone. Perhaps lengths are not the same for all observers. Perhaps simultaneity, the idea that two distant events happen at the same moment, is not universal. These were not conclusions yet. They were suspicions, mere hints, whispers that the stage itself might be flexible. This was a profound shift in thinking. Up to this point, time had been treated as an invisible river flowing identically everywhere, carrying all observers forward together. Space had been treated as a fixed grid, stretching uniformly in all directions. Motion happened against these backgrounds, but the backgrounds themselves never changed. The crisis after Michelson-Morley suggested that this picture might be an illusion created by everyday experience. On human scales, speeds are small compared to light. Differences in time and length are too subtle to notice. The old framework works perfectly well where we live, but physics is not obliged to respect human convenience. As scientists grappled with this possibility, the conversation began to change tone. Instead of asking how to detect the ether more cleverly, Some began asking whether the ether was needed at all. Instead of asking how to preserve absolute time, they asked what would happen if time itself were relative. This was not an easy leap to make. It required letting go of deeply ingrained assumptions, not because they were proven false in daily life, but because they could not survive a single stubborn experiment. The moment is worth pausing on. Physics had reached a point where adding complexity no longer helped. Every patch made the theory heavier, less elegant, more fragile. The simplicity that had guided scientific progress was slipping away. What was needed was not another adjustment, but a new principle. A principle that treated all observers equally. A principle that accepted the constancy of light not as an inconvenience, but as a foundation. A principle that allowed space and time themselves to adapt. This kind of change rarely comes from committees or consensus. It comes from someone willing to take an idea seriously even when it feels unreasonable. The crisis did not announce itself with alarms or declarations. It existed as a tension, a discomfort, a sense that the pieces no longer fit together cleanly. But such moments are often the most fertile. When a framework works too well to be discarded, yet fails too clearly to be trusted, something new is waiting to be born. In hindsight, it is tempting to imagine that the solution was obvious. It was not. Many brilliant minds struggled with the problem. The leap required was not mathematical difficulty, but conceptual courage. The universe had delivered a message through silence. It had refused to reveal an ether. It had refused to privilege any direction or motion. It had insisted calmly and consistently that light speed was the same for everyone. The question was no longer whether this was true. The question was what kind of reality could allow it. In that quiet space of uncertainty, where old ideas had nowhere left to hide, a new way of seeing the universe was about to take shape. One that would not merely explain light, but reshape time, space, and the meaning of now itself. Long before Einstein became a symbol of genius, he was a teenager with an uncomfortable question. It was not the kind of question that appears on exams or in textbooks. It did not begin with numbers or measurements. It began as a simple act of imagination, the kind anyone might attempt while staring out a window or watching sunlight spill across a wall. What would it be like, he wondered, to chase a beam of light? Not metaphorically, literally. Imagine running alongside a beam of light, moving faster and faster, trying to keep pace with it. In everyday life, this idea feels harmless. If you chase a bicycle, it appears slower as you gain on it. If you chase a train, the scenery beside you seems to drift by more gently. Speed, we instinctively believe, depends on perspective. So what if you chased light? If you could somehow run fast enough, light should appear to slow down. And if you matched its speed exactly, something strange should happen. The beam would no longer move away from you. It would hover beside you, frozen in space, like a luminous wave suspended in mid-air. At first glance, this idea feels almost poetic, but there was a problem. By the late 19th century, physicists already had a very successful set of rules describing electricity and magnetism. These rules quietly insisted that light could not behave this way. According to them, light was not a thing that could stand still. A frozen beam of light was not just unobserved, it was impossible. Light, according to these rules, was always in motion. Not usually in motion, not approximately in motion, always. This created a tension that refused to resolve itself. On one hand, intuition said that speeds add and subtract. On the other hand, the rules governing light insisted on something far stranger. No matter how fast you moved, light would still race away from you at the same pace. Einstein took this tension seriously. He did not try to dismiss it as a technical detail or an edge case. He trusted the rules of electromagnetism because they worked. They predicted experiments accurately. They described nature with uncanny precision. If they said frozen light could not exist, then intuition must be the thing that was wrong. This was a subtle but courageous move. Most people, when faced with a conflict between intuition and mathematics, try to adjust the mathematics. Einstein adjusted his intuition instead. If you cannot slow light down by chasing it, then something else must be giving way. The usual assumptions about motion, time, or space must be incomplete. And slowly, almost reluctantly, a radical idea began to take shape. What if light does not change its speed because time itself changes? This idea feels strange because time feels untouchable. We experience it as a steady flow, the same for everyone. Seconds feel universal. Moments feel shared. The present feels like a place we all occupy together. But Einstein realized that this feeling might be misleading. In everyday life, speeds are small compared to light. The differences are too tiny to notice. Time behaves as if it were absolute because for us, it almost is. But nature is not obligated to align itself with human comfort. If light speed is the same for everyone, then the universe must make adjustments elsewhere, and the only place left to adjust is time. This realization did not come with fanfare. It did not arrive as a single flash of insight. It emerged from careful thought, from following a question to its logical conclusion, even when that conclusion felt unsettling. Imagine two people moving differently through space, each chasing the same beam of light. If both measure the same speed for that light, then their clocks cannot agree. One must tick more slowly than the other. There is no alternative that preserves both intuition and consistency. This is not a flaw, it is a necessity. Einstein began to see time not as a universal background, but as something intimately connected to motion. Time would no longer be a single rhythm shared by all observers. It would become personal, shaped by how one moves through space. At this stage, none of this was proven. It was not yet a theory. It was a direction, a suspicion that the universe was structured in a way far stranger than anyone had assumed. What makes this moment so powerful is its humility. Einstein did not begin by claiming that time was relative. He began by admitting that frozen light made no sense. He trusted the behavior of nature more than the habits of human thinking, and in doing so, he opened a door. Once that door was open, the implications began to line up with remarkable clarity. If time could stretch or compress depending on motion, then the strange silence of the Michelson-Morley experiment suddenly made sense. Light speed could remain unchanged because the measuring tools themselves, clocks and rulers, were not as rigid as once believed. This did not feel comfortable. It meant letting go of the idea that there was a single, universal clock ticking away for the entire universe. It meant accepting that simultaneity, the notion that two distant events happen at the same time might depend on who is watching. But it also brought an unexpected sense of order. The universe was not broken. It was consistent. It followed rules that were simple, elegant, and deeply non-intuitive. Light did not need special treatment. It did not need an invisible medium or a hidden exception. It simply revealed the structure of reality by refusing to behave like anything else. In chasing a beam of light, Einstein discovered that the chase itself was impossible. And in that impossibility, he found a clue. Light did not need to slow down. The universe would bend time instead. This was not yet a full answer. It was a starting point, but it was enough to change the direction of physics forever. From here, the pieces would fall into place one by one. Simple rules would be stated, consequences would unfold, clocks would begin to drift, lengths would begin to shrink, and the familiar idea of a shared now would quietly fade. But all of that grew from this single uncomfortable realization. You cannot run beside light, and the reason you cannot has everything to do with time. After the uncomfortable realization that you cannot run beside light, the question became unavoidable. If light always escapes at the same pace no matter how you move, then the universe must be arranged in a very particular way. Einstein's next step was not to invent complexity, but to remove it. He searched for the smallest set of ideas that could explain everything that had already been observed, without contradiction. He arrived at two rules so simple, they almost feel modest. The first rule is about fairness. The laws of nature do not favour anyone. No matter how fast you move, no matter which direction you travel, the basic rules governing motion, electricity, magnetism and light remain the same. There is no privileged observer, no hidden state of rest, no special vantage point from which the universe reveals its true behaviour. Whether you're standing still, walking, riding a train or orbiting a planet, the universe plays by the same rules. This idea was not entirely new. It echoed earlier principles in physics, especially those used to describe motion. What made it powerful here was its insistence on universality. Even light would be included. Even the fastest thing in existence would not break the rule. The second rule was more unsettling. Light speed is the same for everyone, not approximately the same, not the same only when measured carefully, the same, always. Regardless of how the source moves or how the observer moves, this is where intuition begins to resist. In daily life, we're used to adding speeds. If you walk forward on a moving train, someone standing on the ground sees you move faster than someone seated beside you. Motion stacks. Perspective matters. Light refuses to participate in this stacking. If a flashlight is turned on aboard a fast-moving spaceship, the light does not inherit the ship's speed. It does not go faster in the forward direction or slower in the backward one. It leaves the flashlight at the same pace in all directions, as if the ship were standing still. Taken together, these two rules feel harmless. They sound reasonable. They do not mention time slowing down or space shrinking. They make no dramatic claims. And yet, when combined, they leave the universe with very few options. To see why, imagine two observers moving relative to one another, each carrying a clock. Both shine a beam of light between two mirrors, forming a simple light clock. Each observer sees the light bounce up and down, tick by tick, marking time. From each observer's own point of view, everything feels normal. The clock ticks steadily. Nothing seems distorted. But now imagine watching the other observer's clock from afar. From your perspective, their clock is moving through space. The light inside it no longer travels straight up and down. It follows a longer angled path, like a bouncing ball inside a moving train. Here is the crucial point. Light's speed does not change. If the light inside the moving clock must travel a longer path, yet still move at the same pace, then it must take more time to complete each tick. There is no escape from this conclusion. Time, as measured by the moving clock, runs more slowly compared to your own. This is not an illusion. It is not a trick of perspective. It is a direct consequence of preserving light speed while allowing motion. Notice what did not happen here. No machinery broke. No force acted on the clock. Nothing was damaged or altered. The clock simply moved differently through space, and time responded. The same logic applies to distance. Imagine measuring the length of an object moving past you at high speed. To measure its length, you must determine where its front and back are at the same moment. But here, the idea of the same moment becomes slippery. Two observers moving differently do not agree on which events are simultaneous. What feels like a shared Tao dissolves when distance and motion are involved. As a result, lengths measured along the direction of motion appear shorter, not because objects physically compress under stress, but because space and time are intertwined in a way that reshapes measurement itself. This is why it is so important to avoid thinking of these effects as mechanical distortions. Nothing is being squashed, nothing is being damaged. Geometry itself is doing the work. Time stretches, space adjusts, light stays constant. And suddenly the strange silence of earlier experiments makes sense. The Michelson-Morley result no longer looks mysterious. If measuring rods subtly change length, and clocks subtly change rhythm depending on motion, then experiments designed to detect differences in light speed would naturally fail, i.e. not because nature is hiding something, but because it is being perfectly consistent. This realization brings an unexpected calm. Instead of piling exceptions on top of exceptions, Einstein's two simple rules replace complexity with coherence. The universe does not need an ether. It does not need a background grid. It needs only consistency and symmetry. There is a quiet elegance in this. The rules do not tell space how to behave or time how to flow. They simply insist that light speed is sacred and that no observer is special. Everything else follows. What feels radical is not the rules themselves, but their consequences. They force us to let go of the idea that time is universal and that space is rigid. In their place, they offer a reality that is flexible but orderly, strange but reliable. And that it is tempting to think of this as a story about light, but in truth, light is only the messenger. The deeper message is about the structure of reality itself. Time and space are not independent backdrops. They respond to motion. They adapt to preserve the same simple rules everywhere. Once this is accepted, the universe becomes easier to understand, even if it becomes harder to imagine. Clocks drift, not because they are faulty, but because time itself is elastic. Distances change, not because objects are unstable, but because space participates in motion. And beneath it all, light continues to move at its steady, unwavering pace, quietly enforcing a harmony that no observer can escape. From these two gentle rules, an entirely new picture of reality unfolds. In the next stretch of our journey, that picture will become even clearer, as we watch time and space reveal their true relationship through the simplest clock imaginable, one built entirely from light. To understand how time itself can stretch, Einstein did not begin with complex machinery or elaborate mathematics. He began with a clock. Not a clock made of gears or springs, but one made of light. Imagine a simple device. Two mirrors face each other, one above the other. Between them, a single pulse of light bounces back and forth. Each time the light hits the lower mirror, the clock marks a tick. Up, down, steady, reliable, elegant. This clock is special because it measures time using something universal. Light. There are no moving parts to slow down, no friction, no internal mechanism to interfere. If anything can reveal the true nature of time, it is a clock like this. Now imagine standing beside this clock as it rests on a table. You see the light pulse travels straight up and straight down, tracing a simple vertical path. Each bounce takes the same amount of time. The ticks feel even, calm, predictable. From this point of view, nothing seems strange. Now imagine the same clock placed on a train gliding past you at a steady speed. From the perspective of someone riding the train, nothing has changed. The light still moves straight up and down between the mirrors. The clock ticks just as it always has. Time feels normal. But from your perspective, watching from the platform, something subtle happens. As the train moves forward, the light inside the clock does not simply go up and down anymore. It traces a gentle diagonal path. Each pulse travels upward while also moving forward with the train, then downward while still moving forward. The path is longer. Here is where the universe makes its quiet decision. Light speed does not change. If the light must travel a longer path but move at the same pace, then it must take more time to complete each bounce. The tick of the moving clock stretches out. It takes longer between beats. This is time dilation, not because the clock is malfunctioning, not because motion damages it, but because time itself unfolds differently when motion is involved. The clock does not run slow in its own frame. It behaves perfectly. But when compared across different states of motion, time reveals its elasticity. This is not a trick of perception. It is not an illusion caused by delay or signal travel. Even if you could somehow correct for every visual effect, the conclusion would remain. The moving clock truly experiences less time between ticks compared to a stationary one. And this realization is deeply unsettling, because it challenges something we rarely question. We assume that time is shared, that a second is a second everywhere, that now is a universal moment, sweeping across the universe like a spotlight. The light clock quietly disagrees. If two observers move differently, they do not agree on how time passes. And more surprisingly, they do not agree on which events happen at the same time. This loss of simultaneity is perhaps the most subtle consequence of all. Imagine trying to measure the length of the moving train. To do so, you must mark where the front and back are at the same moment. But if the same moment depends on who is moving, then length itself becomes observer-dependent. From your point of view, the train appears slightly shorter along its direction of motion. Not because it is physically compressed, but because the way space and time slice reality into moments has shifted. This is length contraction. Again, nothing is crushed. No force is applied. Geometry does all the work. Time stretches. Space adjusts. Light stays constant. The light clock makes this unavoidable. It is not a special example chosen to exaggerate effects. It is the simplest possible clock, stripped of every complication. If time dilates for a light clock, it must dilate for all clocks. If space contracts in this geometry, it must contract for all objects. There is no preferred clock, no master timeline. And slowly, gently, the idea of a universal now begins to fade. Events that feel simultaneous to one observer are not simultaneous to another who is moving differently. There is no single present moment slicing across the universe. Instead, each observer carries their own sense of now, shaped by their motion through space. This does not mean reality is chaotic or subjective. Quite the opposite. The rules are precise. They are consistent. They apply to everyone equally. What changes is not the reliability of the universe, but our expectation that it should match human intuition. At everyday speeds, these effects are too small to notice. Our clocks agree closely enough. Our rulers behave well enough. The illusion of a shared present holds. But the light clock reveals that this is an approximation, not a truth. And once you see this, it becomes difficult to unsee. Time is not a single river carrying all observers forward together. It is more like a landscape, where different paths trace different durations. Space is not a rigid container, but part of the same fabric, stretching and adjusting to preserve light's quiet rule. The light clock does not argue, it simply shows. And what it shows is that reality is not built from time and space separately, but from their relationship. This realization completes the uncomfortable solution Einstein began as a teenager. Light does not slow down. Instead, the universe reshapes time and space to keep its promise. From this point forward, cause and effect themselves must obey this structure. Not everything can influence everything else. There are boundaries, shaped not by force but by speed. And those boundaries will soon come into view. Once time and space lose their rigid certainty, a new question quietly rises to the surface. If clocks tick differently and now depends on motion, then what does it mean for one event to cause another? What does it mean for something to affect you, or for you to affect the world? The answer is shaped not by force or intention, but by light. Imagine yourself standing perfectly still at a single moment. This moment is yours. It is here. It is now. From this point, the universe begins to divide itself naturally into regions, not by walls or distances, but by possibility. Some events can influence you, some events can be influenced by you, and some events are simply elsewhere, beyond any connection. These regions are not philosophical abstractions. They are drawn by the speed of light itself. To picture this, imagine dropping a stone into a perfectly calm pond. Ripples spread outward in smooth circles. No matter how long you wait, those ripples can only travel so fast. Shores beyond their reach remain untouched. Light behaves in a similar way, but in 4 dimensions instead of 2. From your present moment, light can travel outward into the future. Everything light can reach defines the region you could, in principle, influence. If you turn on a flashlight to send a signal or cause an explosion, its effects are limited by how far light can travel. This region forms a kind of expanding boundary into the future. In the other direction, light from the past travels toward you. Stars shine. Signals arrive. Memories are formed. Everything that could possibly affect you must lie within this region. If light from an event has not had time to reach you, that event is causally disconnected from your present. And then there is the vast remainder. Events that are too far away in space or too close in time for light to connect them to you. They exist, they are real, but they are beyond influence. Neither you nor they can affect one another, no matter how powerful the technology or how patient the observer. These regions are often described using a simple geometric image, one that resembles a pair of cones meeting at a point, but it is more helpful to think of them as borders of influence. The speed of light draws a boundary around every moment, quietly declaring what is possible and what is not. This boundary does not care about desire, urgency, or importance. It is impartial. It treats all events equally. It doesn't speed up for emergencies or slow down for convenience. It simply defines the structure of cause and effect. What makes this idea so profound is that it replaces an absolute sense of time with a relational one. Instead of asking, "What is happening now everywhere?" the universe asks a gentler question. What can possibly be connected? 2 events may feel simultaneous to one observer and separated to another, but causality remains intact. If one event cannot influence another, no disagreement about time can change that. This is how relativity preserves order without relying on a universal clock. Cause and effect are not determined by agreement on time, but by the ability of light to travel between events. If light can connect them, influence is possible. If it cannot, influence is forbidden. There is something quietly comforting in this. Even as time becomes flexible and space becomes dynamic, the universe enforces a firm rule about causality. Effects do not arrive before causes. Messages do not leap across impossible gaps. Reality remains stable, not because it is rigid, but because it is structured. The image of ripples helps here. Imagine standing on one shore, watching ripples spread across a vast lake. Some islands are close enough to feel the wave, others lie too far away. No amount of wishing or shouting can make the ripple arrive sooner. The water simply does what water does. Light does the same, but through space-time. This perspective also reshapes how we think about the present moment. Your now is not a slice across the universe. It is a point surrounded by a growing sphere of future possibility and a receding sphere of past influence. Everything else exists in a quiet elsewhere, and neither past nor future relative to you, but simply disconnected. This does not make the universe smaller, it makes it more honest. We're used to imagining that everything exists together in a shared moment, even if we cannot see it. Relativity suggests something subtler. Connection matters more than simultaneity. Influence matters more than agreement. The borders drawn by light are not limitations imposed on us. They are the grammar of reality. Without them, the universe would be vulnerable to contradiction. Effects could arrive before causes. Stories could unfold backward. Logic itself would fray. Instead, the universe chooses calm consistency. Every observer carries their own borders of influence, shaped by motion and time. And yet, all observers agree on one thing: causality holds. The structure remains intact. This is why relativity, despite its strangeness, is not chaotic. It is deeply ordered. It replaces rigid absolutes with relational boundaries that quietly protect reality from paradox. As we drift deeper into this understanding, another question naturally arises. What if something could cross those borders faster than light? What if a message could slip through the boundary before the ripple arrives? The answer to that question reveals why the universe guards its speed limit so carefully, and why, beneath all its flexibility, reality remains remarkably well behaved. Once the borders of influence come into view, a tempting question appears. If light defines what can affect what, then what would happen if something could outrun it? At first, this sounds like a technical curiosity, a problem for engineers or science fiction writers. But beneath the surface, it is a question about logic itself, about whether the universe allows its own story to be told out of order. To see why this matters, imagine a simple exchange. You send a message, someone receives it. They reply. This sequence feels obvious, because comes before effect. Question comes before answer. Even when messages travel slowly, the order remains intact. Now imagine a signal that moves faster than light. Not just slightly faster, fast enough that from some points of view it arrives before it was sent. This is not a trick of wording. It is a direct consequence of relativity. Because time is not universal, different observers disagree on the order of distant events. If a signal could cross the borders defined by light, then there would always be some observer for whom the effect appears to precede the cause. In one frame of motion, you send the message and later receive a reply. In another frame, the reply arrives first. In yet another, the message never seems to be sent at all. The story no longer has a consistent order. This is where intuition begins to falter, because we are not used to thinking of logic as something that depends on speed. But in a universe where time and space are intertwined, speed becomes the guardian of the order. If faster-than-light signals were possible, the borders of influence would dissolve. The careful structure that separates past, future, and elsewhere would blur. Events could slip across boundaries meant to protect them, and once that happens, paradox is no longer an abstract idea. It becomes unavoidable. Imagine receiving an answer to a question before you have asked it. Imagine acting on information that has not yet been created. Imagine preventing the very message that warned you to prevent it. These are not clever puzzles, they are contradictions. The universe, as far as we can tell, does not tolerate contradictions. This is why the speed of light acts like a firewall, not a barrier meant to frustrate curiosity, but a boundary that preserves consistency. It ensures that causes remain causes and effects remain effects, no matter how observers move. It's important to notice something subtle here. The universe does not forbid faster-than-light motion because it is too hard or too energetic. Those explanations come later. At a deeper level, it forbids it because allowing it would break the logic that makes reality intelligible. Light speed is not merely a property of light. It is a structural feature of space-time itself. This is why attempts to imagine faster-than-light travel often feel slippery. They require loopholes, shortcuts, or hidden assumptions. They rely on bending space in exotic ways or invoking entities that have never been observed. And even then, the rules push back. Whenever something appears to move faster than light, closer inspection reveals that no information has actually crossed the boundary. Shadows can sweep across distant surfaces faster than light, but they carry no message. Patterns can shift rapidly, but nothing meaningful is transmitted. Even in the strange realm of quantum entanglement, where particles share correlations across vast distances, the rule survives. The outcomes are linked, but no usable signal travels between them. There is no way to send a message, no way to choose the outcome, no way to control the connection. The universe allows correlation without communication. This distinction is crucial. It preserves wonder without sacrificing order. The idea of faster-than-light motion is seductive because it promises freedom. Freedom from delay, freedom from isolation, freedom from the vast, quiet distances between stars. But the universe seems to value coherence more than convenience. By enforcing a speed limit, it ensures that every observer, no matter how they move, agrees on the fundamental structure of cause and effect. They may disagree about timing, they may disagree about simultaneity, but they will never disagree about what can influence what. There is something almost gentle about this rule. Instead of collapsing under the weight of its own complexity, reality maintains a simple constraint that keeps everything in balance. The speed of light becomes a kind of rhythm, setting the tempo at which stories can unfold. Nothing can rush ahead of the narrative. Nothing can skip to the end. This is not a limitation placed upon us alone. It applies to everything, to particles, to stars, to information itself. The universe plays fair. And perhaps this is why relativity, despite its strangeness, feels so stable. Time can stretch, space can bend, observers can disagree. But the story never contradicts itself. The order of cause and effect remains intact. When you hear that nothing can travel faster than light, it is tempting to hear it as a wall. It is better to hear it as a promise that reality will not unravel, a promise that effect will not outrun causes, a promise that the universe, however strange, remains trustworthy. As we move forward, this promise will reveal itself not just in thought experiments, but in everyday technology and daily life. The rules that protect logic are not distant abstractions. They quietly guide the clocks in our pockets and the signals above our heads. And that makes the speed of light feel less like a restriction imposed on us and more like the quiet architecture holding reality together. After all the thought experiments and quiet logical necessities, it is natural to wonder whether any of this truly touches the world outside our imagination. Time stretching, clocks disagreeing, different nows. These ideas sound delicate, almost philosophical, and yet they have been tested, repeatedly, thus carefully, in ways that leave very little room for doubt. Relativity is not something we merely believe. It is something we use. One of the earliest confirmations came from clocks themselves. In the 20th century, scientists built clocks far more precise than anything that had existed before. These were not clocks with hands and springs, but clocks based on the rhythm of atoms. They ticked with astonishing regularity, sensitive enough to notice differences smaller than a heartbeat could ever reveal. With these clocks, an experiment became possible. Take two identical atomic clocks, keep one on the ground, place the other on an airplane and fly it around the Earth. Then bring them back together and compare them. According to everyday intuition, the clocks should agree. They started together. They experienced the same journey. The time should have passed equally for both. But relativity predicted otherwise. The clock that moved would experience time slightly differently. Its motion would cause its internal rhythm to slow by an almost unimaginably small amount. Too small to notice without extraordinary precision, but not too small to exist. When the experiment was performed, the result was clear. The clocks disagreed, not by much, by tiny fractions of a second, but the difference matched the prediction. Not approximately, not vaguely, precisely. Time had passed differently. No interpretation was required, no philosophical argument. The clock simply told the story. Another confirmation arrived from the sky. High above Earth's surface, cosmic rays constantly strike the atmosphere, producing showers of short-lived particles. Among them are particles called muons. These particles are unstable. Left alone, they decay quickly, vanishing in a fraction of a second. According to classical thinking, most muons should disappear long before reaching the ground, and yet detectors on Earth record them regularly. The explanation lies in motion. From our perspective, the muons are racing toward Earth at extraordinary speeds. Because of this motion, their internal clocks tick more slowly relative to ours. Their brief lifetimes stretch just enough for many of them to survive the journey. From the muon's own perspective, nothing unusual happens. Its lifetime feels normal. Instead, the distance it must travel appears shortened. Time stretches. Space adjusts. Light remains constant. The same rules apply, regardless of scale. Perhaps the most familiar confirmation of all sites quietly in your pocket. Global positioning systems rely on satellites orbiting Earth. These satellites carry extremely precise clocks. To determine your location, your device measures how long signals take to travel from multiple satellites to you. This process depends on timing accuracy down to billionths of a second. And here, relativity becomes unavoidable. The satellites are moving relative to Earth. Their clocks experience time slightly differently. They're also higher in Earth's gravitational field, which introduces another subtle shift in how time flows. If these effects were ignored, the system would drift. Not slowly, but rapidly. Errors would accumulate, growing by kilometers each day. Navigation would fail. Instead, engineers account for relativistic time differences as part of normal operation. The clocks are adjusted before launch. Corrections are applied continuously. Relativity is built into the infrastructure of modern life. This is not exotic physics, it is maintenance. Time dilation is not a strange side effect reserved for thought experiments. It is a practical reality, quietly compensated for every moment. What is remarkable is not that these effects exist, but that they are so consistent. Whether measured with flying clocks, cosmic particles, or orbiting satellites, the same pattern appears. Motion affects time. Not because of wear, not because of stress, but because of how reality is structured. These confirmations carry a quiet emotional weight. They tell us that the universe is not pretending. It is not offering clever illusions that vanish under scrutiny. It behaves exactly as relativity describes, as even when the differences are too small for human senses to detect. The world works this way whether we notice or not. And there is something comforting in that reliability. Relativity does not undermine everyday life. It supports it. It does not pull the rug out from under reality. It quietly reinforces it with precision. Time can stretch without chaos. Space can adjust without collapse. Clocks can disagree without confusion. Everything remains consistent because the rules are consistent. When people say that relativity is just a theory, they often mean that it is abstract or untested. In science, the word theory means something very different. It means a framework that has survived every attempt to break it. Relativity has been tested in laboratories, in the atmosphere, in orbit, and deep in space. Each time, the universe responds the same way. Light keeps its pace. Time adapts. Causality holds. These everyday confirmations prepare us for something important. If the rules hold so firmly in small familiar settings, then they will hold just as firmly at the edges of the cosmos, in distant galaxies, in extreme environments, in places we can only imagine. And yet, sometimes, it appears as if the rules are being bent. Signals seem to arrive too quickly. Connections seem to form across impossible distances. When that happens, the universe is not breaking its promises. It is inviting us to look more closely. By now, the rules have revealed themselves clearly. Light sets a pace. Time adapts to protect it. Causality remains intact. And yet, every so often, we encounter stories that seem to whisper otherwise. Stories of particles connected across vast distances, of signals that appear to outrun light, of light itself being slowed, frozen, or stopped. At first glance, these ideas can feel unsettling. If the universe guards its speed limit so carefully, why do these situations exist at all? The answer is quieter than the headlines suggest. Most apparent violations of the speed of light are not cracks in the rules. They are misunderstandings of what the rules actually govern. The first and most famous example comes from the world of quantum physics. Quantum entanglement is often described as a mysterious link between particles, one that persists no matter how far apart they are. Measure one particle, and the other seems to respond instantly, even across galaxies. This sounds like faster-than-light communication, but it is not. The key detail lies in what is being shared. Entangled particles share correlation, not information. When one particle is measured, the outcome is random. There is no choice involved. No message is sent. No signal is controlled. Only when the two observers later compare their results, using ordinary communication limited by light, does the pattern reveal itself. The universe allows shared structure without shared messages. This distinction preserves causality. Nothing useful travels faster than light. Nothing can be used to send a warning, a command, or a secret across the boundary of influence. The silence remains intact. Another illusion arises in astronomy. Sometimes distant objects appear to move faster than light across the sky. Jets from active galaxies seem to sweep outward at impossible speeds, and shadows cast by rotating beams can race across distant surfaces faster than any signal could. But here again, nothing physical outruns light. These effects arise from geometry and timing. When light from different parts of a moving structure reaches us at different moments, motion can appear exaggerated. The pattern moves faster than light, but no particle does. No information travels with it. It is like the shadow of a bird flying across a mountain range. The shadow may move swiftly, but the bird itself remains bound by its own limits. The universe allows fast patterns. It forbids fast messengers. Then there is the idea of slowing light itself. In certain exotic materials, scientists have managed to reduce the speed at which light pulses travel. In some cases, they have brought light almost to a standstill, storing it briefly before releasing it again. At first, this sounds like a contradiction. If light can be slowed, then perhaps its speed is not truly constant. But what is being slowed here is not the fundamental signal. It is the way the material responds. Inside these materials, light interacts with atoms, momentarily absorbed and re-emitted. The message does not outrun light. It takes a more winding path, pausing along the way. The underlying limit remains untouched. The universe still enforces its rule. Information does not escape the boundary. There are also ideas that live entirely in theory. Warp drives, wormholes, hypothetical particles that always move faster than light. These ideas are fascinating and they make for compelling stories, but they come with conditions so extreme or assumptions so untested that they remain speculative. And even within these ideas, the rule pushes back. Many require forms of matter that have never been observed. Others demand energy arrangements that may be impossible, and nearly all of them struggle to preserve causality without introducing contradictions. The universe seems willing to bend space, stretch time, and twist geometry, but it remains deeply reluctant to allow signals that outrun light. This reluctance is not arbitrary. As we've seen, the speed of light is not just about brightness or illumination. It is about the shape of cause and effect. It is about maintaining a consistent story, one where actions lead to consequences without looping back on themselves. Whenever something appears to break the rule, closer inspection reveals that the rule was never violated. It was only misunderstood, where this is an important emotional moment in the journey. Up to now, relativity may have felt strange but orderly. These apparent exceptions test our trust. They invite doubt. They tempt us to believe that the universe might be less coherent than it seems. Instead, they reveal the opposite. The rules are not fragile. They are resilient. They survive the strangeness of quantum physics. They survive the vast scales of astronomy. They survive human ingenuity and imagination. Every test so far has reinforced the same conclusion. Light speed remains the limit for influence. Time adjusts to preserve it. Reality stays consistent. There is a quiet elegance in this persistence. The universe does not shout its rules. It demonstrates them patiently, again and again, across different domains, scales, and experiments. And perhaps that is why relativity feels less like a theory and more like a framework. It does not compete with new discoveries. It absorbs them, placing each into a larger, calmer structure. As we move toward the final stretch of this journey, the focus begins to widen. If time is flexible, if space is dynamic, and if causality is carefully shaped by light, then what does this mean for the universe as a whole? What does it mean for distant galaxies, for cosmic history, and for the feeling that the universe is vast, quiet, and strangely lonely? The rules that protect logic also shape our horizons, and in doing so, they quietly define what it means to live inside a universe with a speed limit. By this point in the journey, time has already loosened its grip. It stretches, it slows, it adjusts itself depending on motion and gravity. And yet, there remains one idea about time that feels especially difficult to release: the idea of a shared present. In everyday life, now feels obvious. It feels like a moment the entire universe occupies together. When you glance at a clock, you instinctively imagine that the same moment is unfolding everywhere else, on distant streets, in faraway cities, even across the stars. Relativity gently suggests otherwise. The loss of a universal now does not arrive as a dramatic declaration. It slips in quietly as a consequence of everything that has already been accepted. If time passes differently for different observers, and if simultaneity depends on motion, then there is no single slice of time that all observers can agree upon. Two events that feel simultaneous to you may not feel simultaneous to someone moving differently. Neither observer is wrong. Each is simply tracing time along a different path through space-time. This idea can feel unsettling at first. It seems to challenge the sense of shared experience that anchors us to one another. But relativity is not saying that moments are unreal. It is saying that the universe does not privilege one definition of now over another. Time, in this view, is not a spotlight sweeping across the cosmos. It is not a river carrying everything forward in lockstep. It is more like a landscape. In this landscape, every event has a place. Past, present, and future are not erased or invented by observation. They simply exist as parts of the terrain. Different observers walk different paths through it, yet encountering events in different orders, at different rhythms. This way of thinking is often called the block universe. The name sounds rigid, But the idea itself is surprisingly gentle. It does not insist that the future is fixed or that choice is an illusion. It simply suggests that time, like space, is part of the structure of reality rather than a flow imposed upon it. In a map, all locations exist at once. North does not become south. East does not wait for west. Movement happens through the map, not to the map. Time, in the block universe view, behaves similarly. Events do not come into existence when they are observed. They occupy positions in space-time. Observers move through these positions, experiencing them as past, present, or future depending on their path. This perspective can feel strange because it contrasts so sharply with human experience. We feel time passing. We feel moments arriving and leaving. Memory flows in one direction. Anticipation points forward. Relativity does not deny this experience. It explains it. The flow of time is something that happens within consciousness, not something imposed by the universe as a whole. The structure of space-time allows many paths, many rhythms, many definitions of now, all equally valid. There is no master clock ticking at the center of reality. This does not make the universe cold or impersonal. If anything, it makes it more inclusive. Every observer's experience is honored. No single perspective is elevated above the rest. And importantly, causality remains intact. Even in a block universe, causes still precede effects along every observer's path. The borders defined by light still apply. You cannot influence events outside your reach. The structure remains orderly, even if the notion of a shared present dissolves. For some, this idea feels liberating. If time is a landscape, then moments are not lost. They are not erased when they pass. They remain part of the structure, accessible in memory, influence, and consequence. The past does not vanish. The future does not rush toward us. Everything simply is. For others, this idea feels unsettling. It challenges the comfort of believing that the future is open in the same way the past is closed. It invites questions about choice, freedom, and meaning. Relativity does not answer those questions for us. It does not insist on a single interpretation. It offers a framework and leaves room for reflection. This is why it is important to approach the block universe as a way of seeing, not a rule to obey. It is a lens, not a verdict. You can accept that there is no universal now without giving up the experience of living in the present. You can accept that time is part of a larger structure without denying the importance of moments. In fact, this perspective can make the present feel more precious. If there is no single cosmic moment shared by all, then your now is uniquely yours. It is shaped by your motion, your history, your place in the universe. It is not diminished by the absence of a universal clock. It is defined by it. As the universe grows larger in our understanding, it does not push us aside, it accommodates us. The idea that time is a landscape rather than a river does not demand belief. It invites quiet contemplation. It asks us to sit with the possibility that reality is richer, deeper, and more subtle than our instincts suggest. And perhaps that is the most fitting place to pause, not at a conclusion, but at an opening. Because once we release the need for a shared present, we can begin to see the universe not as something rushing forward, but as something held together by structure, consistency, and gentle limits. Those limits shape our horizons. They define what we can see, what we can reach, and what must remain distant. And in that vast, quiet structure, the speed of light continues to whisper its steady rule, not as a barrier, but as the rhythm that gives the universe its form. When you step back from all the details, the equations we never wrote, the clocks we imagined, and the borders we traced with light, one simple fact remains. The universe has a speed limit, At first, this can feel disappointing. A limit sounds like a barrier, a rule imposed from above, something that prevents us from reaching farther, connecting faster, knowing more. But as we've seen, this limit is not an obstacle placed in our way. It is the quiet structure that gives the universe its shape. Because light travels at a fixed pace, the universe has depth. Distance matters. Time matters. The night sky is not a flat image painted above us, but a layered archive of history. When we look at distant stars, we're not seeing where they are now. We're seeing where they were, long ago. Some of that light began its journey before life existed on Earth, some before our planet had even formed. The sky is a record, written in light, arriving line by line. This delay is not a flaw in perception. It is what allows the universe to have a past at all. If information travelled instantly, everything would collapse into a single moment. There would be no unfolding, no sequence, no story. Cause and effect would blur into simultaneity. History would lose its meaning. The speed of light protects time itself. It also explains why the universe feels vast and quiet. Between stars lie enormous distances. Even travelling at light's pace, messages take years to cross them. Conversations between civilizations, if they exist at all, would be slow, patient affairs, stretched across generations. This cosmic silence is not emptiness. It is spacing. The universe gives events room to exist independently. It prevents everything from happening all at once. It allows complexity to develop locally without immediate interference from everywhere else. In this sense, the speed of light is not isolating. It is enabling. It allows stars to live out their lifetimes. It allows planets to settle into stable orbits. It allows life to emerge without being overwhelmed by distant chaos. Even on smaller scales, this limit shapes our experience. When you speak, your words take time to reach another person. When you act, the consequences spread outward gradually. Nothing erupts everywhere at once. Reality unfolds in layers, giving meaning to proximity and sequence. This is not an accident. It is design at the deepest level. As our technology advances, we often feel impatience with this limit. We imagine instant travel, instant communication, instant understanding. But the universe seems uninterested in instant anything. Instead, it offers consistency. No matter where you are, no matter how you move, the same rule applies. Light keeps its pace, time adapts, space participates, causality holds. This consistency is what allows us to trust reality. We may not share a universal now. We may not agree on the passage of time, but we all inhabit the same structure. The speed of light ties everything together without forcing it together. It is the reason the universe feels large instead of crowded. It is the reason events feel ordered instead of tangled. It is the reason stories have beginnings, middles, and ends. When viewed this way, the speed of light begins to feel less like a ceiling and more like a foundation. It does not sit above reality, constraining it. It runs through reality, holding it together. Every clock that ticks differently, every ruler that subtly adjusts, every boundary of influence we traced earlier, all of them exist to honour this single steady pace, and that pace never hurries. Light moves as it always has, indifferent to ambition, urgency, or desire. It carries information faithfully, never skipping steps, never leaping ahead of cause and effect. In a universe that can stretch time, bend space, and dissolve the idea of a shared present, this constancy is almost comforting. It gives the cosmos a rhythm, a whisper that says, "This is how fast stories may travel." Perhaps that is why, when we look out into the night, the universe feels calm rather than frantic, vast rather than chaotic. quiet rather than empty. Everything is happening, but not all at once. The speed of light ensures that there is always time for things to become what they are. And within that structure, within that gentle limit, life finds space to exist, to think, to wonder. We live inside this speed limit not as prisoners, but as participants. Every moment you experience is shaped by it. Every sight, every signal, every memory arrives on light's patient schedule. The present you inhabit is the result of countless journeys completed at exactly the same pace. Reality holds together not through force, but through consistency. And when you let that idea settle, when you stop seeing the speed of light as a wall and begin seeing it as a frame, something shifts. The universe feels less like a place rushing toward an unknown end, and more like a carefully structured story, unfolding at a pace that makes meaning possible. A story where nothing arrives too soon. A story where causes are never outrun by effects. A story held together by a constant whisper, moving always forward, never faster than it should. And in that whisper, the universe remains vast, quiet, and beautifully intact.